Hi everyone. So as always, we start with the learning objectives. Remember, I will put them up again at the end of the video, so you don't need to go through this very thoroughly, just to get a general idea of what we're going to talk about. And the two main concepts that we're going to be dealing with today are fields and forces, namely the electric and gravitational field and force. And what we're going to discuss is how we calculate these forces, and we're going to define fields in a more rigorous way than we've done so far. And then what we're going to learn is to add up the fields created by different particles at a certain point. So imagine that you were born 300 years ago. And you go and ask somebody why things fall. So, here's a little tree. Here's an apple, and you notice that apples fall, right? So they go from here to the ground. And here's this guy, let's call him Aristotle, and you ask Aristotle, why do things fall, Aristotle? And he'd say something that he'd consider obvious, right? Because they're heavy. And you'd be like, well, yeah, but why do heavy things fall? And the answer is like, well, that's what heavy things do. They're defined by their tendency to fall. Their natural place is the ground. Therefore, when you place them above the ground, they will fall. Now, if you asked this same person, Aristotle, about why the moon circles around the Earth, they would come up with a very, very different answer to the one you're used to today, right? So they'd say something like, well, the Earth is here, and then there's these spheres around the Earth, and these spheres are rotating this way, or that way, if you have a different sphere. You have a set of spheres, and each planet is in one sphere, and then they just move around the Earth like that, and that's why they spin. So one thing that you should realize is that there is absolutely no relationship between the way that planets move and the way that things fall in the mind of this person that lived 300 years ago, in the mind of this Aristotle guy. So in order to understand the revolution that the law of gravitation represented, you need to put yourself in that worldview where there's one law for apples and people, and there's another law completely different for the moon and the planets and so on. And it makes sense, right? That they're completely detached from the Earth. How could I possibly apply the same laws to planets, these things that I see in the sky, that I apply to something as common as a glass? It makes no sense. And that's why Newton was so revolutionary. So what he said was like, well, guess what? I can actually explain why apples fall and why planets attract using exactly the same law. So there's two reasons why this is revolutionary. Reason number one is he unified heaven and earth. Right? So first there was the earth, and then there were the heavens around it, and they were in completely different spheres, metaphorically and literally. And suddenly he goes and says, no. Look, you can apply the same laws to the earth that you apply to the heavens, and everything works out. There is no discontinuation. The earth is a part of the heavens. And that's amazing. Suddenly our universe gets expanded so much more. That's the first part. That's why this was so revolutionary. The second reason this was so revolutionary is that he not only said these two things follow the same law, but he actually went and came up with the law. And said to people, not only this is true, but here's a law, and you can use it to calculate how planets move, and you can use it to calculate how apples fall, and everything's going to work out. And people did, and people calculated, and everything worked out. And people were really impressed, so much so that Newton dominated European thought for the next 200 years and still does today in a way. I'm telling all of this to you because for most of you, gravity right now may be something that's obvious, but it was not obvious at all to most of humankind for most of our history. Now, what you hopefully know already about gravity is that if I have two bodies with two different masses, so let's call this mass big M and this mass small m, they attract each other, right? And that the bigger they are, the more they attract each other. So this little guy here will push this guy this way, and this big guy here will push this guy this way. And hopefully you know that the further apart these two guys are, so this distance here, the bigger it is, the smaller the force. Right? Because if, for example, if I go to the moon, I can barely feel the Earth's attraction, which means that somehow the force gets smaller with the distance. I also cannot feel the sun's attraction from the Earth, right? Now, just knowing this, I would like you to try to come up on your own for a formula that can express this idea that the force is proportional to both masses and inversely proportional to the distance. And if you stop the video and try this out now, you should come up with something that's pretty close to what Newton actually did. Now, here's the actual formula, and here's how you derive it. First thing, force, because this is a force, should be equal to, well, the more mass, the more force. So should it be multiplying or dividing? I think I heard you say multiplying. Well done. So mass is multiplying, and this other mass, again, the more mass, the more force, so it should also be multiplying. Yay! And then remember that when I don't write anything in between, it means it's multiplying. Now, because force gets smaller with the distance, should it be multiplying or dividing? And hopefully I just heard you say dividing. So I have the distance here dividing. And now I'm almost done. Now it turns out that nature, unfortunately, does not use kilograms and meters for its units. So we somehow have to transform from our units to nature's units. And to do that, we use a constant of proportionality, which we're going to call G, which is the gravitational constant. And also I'm going to put a minus sign here, though you may see me omitting it from time to time, because at the end we only care about the total size of the force. And I put this minus sign here, meaning that the force is always attractive. Sometimes this will be important, especially when you deal with vectors. Most of the time you can ignore it and just focus on this part here. We're not done yet though, because this distance here could be negative, right? So if I placed this mass over here, the r would be negative, because remember, to this side is positive, to this side is negative. And we don't want this to happen, because the force should always be the same. One way to get rid of this is to just square the distance. Another way to think about this is that the force coming out of this guy gets spread out over a larger area. And this area turns out to be the area of a sphere, which, as you know, is 4 pi squared. 4 pi r squared, sorry. Therefore, since the force gets spread out over a larger area that goes with r squared, it stands to reason that the force decreases with the area, which is r squared. So there you go. Two ways of arriving at the same conclusion. Now, the value of G is extremely small, especially when you compare it with the electric force that we're going to discuss later. But G is equal to 6.67 times 10 to the minus 11. Now, before I write the units, I'd like you to try to figure them out yourself. So, using that, this has to be newtons, these are kilograms, and these are meters. Can you stop the video and try to figure out the units of G? Now, hopefully you just did this. I'll show you how I would do this. So, we know that the units of force have to be newtons. So, newtons have to be equal to the units of G, that we don't know, times, now, these are kilograms, so kilograms squared, times kilograms squared, and divided by this, which is meters squared, right? Now, this is just a simple equation that I can solve, and I get that the units of G are newtons meter squared divided by kilogram squared. Therefore, the gravitational constant is 10 to the minus 11 newtons meter squared divided by kilogram squared. And hopefully you could figure this out on your own. Now, hopefully you remember from when we did electricity that we needed something called a field to explain the fact that if I put a mass over here, it instantly feels a force that pulls it towards here. And nobody likes that. Remember that we called it spooky action at a distance, which means that somehow this mass is capable to act on something that is arbitrarily far without any delay whatsoever. And that is something that physicists don't like, because we know that there's a maximum speed limit, which is the speed of light, and nothing should travel faster than the speed of light, certainly not forces. So what we need to do is to come up with another idea similar to the electric field for gravity. And we call this, of course, gravitational field. And the idea is just that this guy, again, creates some kind of web around itself. So something that will attract any other mass that I put around it. And it will pull it towards this mass. So that it's not this that's doing the force, but the field that this thing is created around itself that's doing the force. Now, again, what we see is that we can't use the formula for the force, because now we only have one object, right? We have this guy here that's creating this thing called a field. So we need to find out some expression that only depends on this guy and not on whoever is receiving the force. So what do? Well, we think of it this way. So let me just get rid of this. So just like we did with the electric field, what we would now like to know is, imagine that I put a certain mass at this point, but I don't know its mass, any mass. How much force will it feel? So how much is it going to get pulled this way? Right? And the answer is, it will depend on the mass of this guy here. Therefore, I can't really answer this question, but what I can answer is how much force this guy will receive per unit of mass, right? So here's what I do. I take my formula for gravitation. So we had F equals gm divided by r squared, and remember, if there's no sign, it means that it's multiplying by default, so this is multiplying. And what I think is, well, if I want to know the force per unit mass, all I need to do is remove one of the masses, right? So I got the expression for the gravitational field strength that I'm going to call G, simply as Gm divided by r squared, which makes sense, right? The more mass I have, the more force this thing is going to do to whatever I put around it. The larger the distance, the less force. And G, again, is just a constant. Now, what I'd like to ask myself is, what are the units of this gravitational field strength? Well, in theory, the units of G will be those of force, because we had force before, divided by units of mass, right? So those are newtons, and those are kilograms. So the units of G will be newtons per kilogram, which makes sense. But here's the catch. Now remember that force equals mass times acceleration, right? So this is telling you that 1 Newton is 1 kilogram times meter per second squared. And therefore, 1 meter per second squared is equal to 1 Newton per kilogram, which is just what we have here. Therefore, the units of the gravitational field not only are newtons per kilogram, but they're also an acceleration. And that's why we speak about the acceleration of gravity on the surface of the Earth. It's the value of the gravitational field strength at the surface of the Earth. And it's also an acceleration. It tells us how much any body that I place at the surface of the Earth is going to be accelerated downwards. And that's amazing. No other field does that, only gravity. And in fact, it was this insight that was used by Einstein to derive his theory of general relativity. All right. So now what I would like you to do is to stop the video for a moment and think. Is the gravitational field strength a scalar or a vector? Now remember, with a scalar, we don't care about the direction. So for example, temperature, 27 degrees. Where is it pointing? It's pointing nowhere. It's just 27 degrees, right? Vector, velocity. It doesn't only matter how fast I'm going, but in which direction. So is the gravitational field strength a scalar or a vector? Now, hopefully you arrived at the right conclusion, which is that the gravitational field strength is a vector. And the reason why it's a vector is that it shows us where the force done on a certain object would go. So if I have an object over here, then I want to know where the gravitational force is going to pull it. And of course, being pulled this way is completely different from being pulled this way. So I not only care about how hard this thing is being pulled, but also in which direction. Right, so what happens if I have two masses, for example, and I want to know the gravitational field here? Now, this is like two children, each one is pushing in its direction, right? So this guy wants the body that's here to go this way, this guy wants the body that's here to go this way, and one of them has to win, right? Now, luckily for us, gravitational field strength is the vector. So all we have to do is add the vector for each gravitational field strength. So let's imagine that we're at this point and we want to know the total field strength. Now, first I'm going to look at the force that this guy does, and because it's so big, let's imagine that it's a big arrow pointing this way. Now, if I want to know the force that this guy does, it will be a little arrow pointing this way. Now, the next thing that I want to do is to add up these two vectors. Now, of course, I can do this mathematically, and I would expect you to when you actually do problems, but just to show you how I would add them up here graphically, we just use the parallelogram rule, right? So remember, we build a parallelogram that has these vectors as sides, and the total vector goes from here to the tip of the parallelogram. So in this case, there would be a net force pointing this way. Now what I would like to do now is to calculate the gravitational field strength at the surface of a planet, so over here. And I'm going to assume that this planet has a certain radius r and a certain mass m. Now this problem becomes very, very easy once you know that if I am located anywhere above the surface, the gravitational force that this planet will exert will behave exactly as if all the mass was located at one point here in the middle. Now, once you know that, things get really, really straightforward. Let me show you. So, all we have is that gravitational field strength is Gm divided by r squared. And then, of course, we want this at r equals r, where the big R is the radius of the planet. So then G equals Gm divided by r squared. And that's it. Pretty much that's the gravitational field strength at the surface of a planet. If we know the radius of the planet and we know the mass of the planet, we can calculate it. As easy as plugging numbers in. Speaking of plugging numbers in, what I would like you to do now is to calculate the field strength at the surface of the Earth. And hopefully once you do it, you will get exactly the value that you know and love of 9.81 meters per second squared. So knowing that m of the Earth is equal to 5.97 times 10 to the 24 kilograms, and knowing that the radius of the Earth is equal to approximately 6,371 kilometers, and remember that G equals 6.67 times 10 to the minus 11 newtons meter squared divided by kilogram squared, you can just plug the numbers in and show that G equals 9.81 meters per second squared. And even though, of course, this is expectable, for someone who just derived this law and using an approximation for these values, getting the actual acceleration of the gravitational field on Earth, I mean, imagine how that must have felt. Now I'd like to talk about a different type of field that you've encountered before, which is the electric field. And you'll see that there are many, many similarities between the gravitational field and the electric field. So many, in fact, that many people suspect there's something fishy going on, that they have to be related in a certain way. Now remember, you should know this already from our last lessons, that there's two types of charges, there's plus and minus charges. If they're the same charge, they repel. If they're different, they attract. And that if I have a certain amount of charge, so for example, a bunch of electrons, I cannot destroy them or I cannot create extra. So however many electrons I have now, that's as many as I'm going to have in 10 million years. Now, also remember that conductors let current flow and insulators don't let current go through. So what we'd like to study now is the force between two charges, let's say big Q and small q. And this force was studied by Coulomb, who knew about Newton's work. And in fact, there's a lot of people who think that his experiment wasn't so precise and he kind of messed with the numbers so that he could get something that looked just like Newton's law. But we're going to pretend he didn't do that, because actually he did get the right answer. So we have two charges here, and we want to know the charge between them. And just like with gravity, we know that the more charge we have, the more force, the more the distance, the less force. So we should expect to see something extremely similar. Now again, all we need to do is, okay, let's say the force will be equal to, well, we have the more charge, the more force. So charge should be multiplying. Now this other charge, if everything is symmetrical, again, the more charge, the more force. So charge should be multiplying. And then the more distance, the less force. So let's put the distance dividing. And again, because the distance could be negative, like for example, I could put this guy there, but we shouldn't care, then this should be squared. And again, we need a constant. And in this case, we're going to call it K. Now the value of Coulomb's constant is huge. So K is approximately equal to 8.988 times 10 to the 9, which is 20 orders of magnitude larger than the gravitational constant. So you can imagine how much stronger this force is than gravitation. Now I encourage you again to figure out the units on your own. So pause the video, figure out the units, and then see how I do that. Now again, remember that these units have to be newtons. Here I have coulombs, here I have coulombs, and here I have meters squared. Remember that the unit of charge is coulomb. So this should be then newtons, because that's what we want to get, times meters squared, to get rid of the meter squared under here, and divided by coulomb squared. And there you go. This is the value and the units of Coulomb's constant. And again, we need to talk about the field strength, which just means that if I put a charge here, it's going to feel a force this way automatically. And my theory is that this force is not really produced by this charge, but by the field created by this charge. And just like in gravity, the field told me the amount of force per unit of mass, in this case, what I want to know is the amount of force per unit of charge. Just makes sense, right? Because the more charge, the more force. So if I know how much force per unit of charge, and I know the charge here, I know exactly the force. So I'm going to do exactly the same as before. I have my force, which is K, big Q, small q, divided by r squared. And just like before, I get rid of one of the q's. And I have the formula for electric field strength, which will be, and we call this E for electric, KQ divided by R squared. Now notice a couple of things here. In the gravitational case, this couldn't be negative and this also couldn't be negative, which means that the force always points the same way, in this case towards the mass. But here things can change, right? So this can be positive and this can be negative, and then this will be negative, and this means that the force will be attractive, and this can be positive and positive, and then the force will be repulsive. Same thing for the electric field. A charge that's negative will create an electric field that will attract test charges, and remember that a test charge is a charge of 1 Coulomb positive, and a positive field will have a positive value for the electric field and therefore will repel test charges, which is exactly what we would expect. So here you see that the signs in the charges already take care of the direction, which is a very, very good property to have. Now, you should barely have to think to answer this question. Is the electric field strength a scalar or a vector? And again, we care about the direction, and therefore it's a vector. And this means, again, that we can add them as vectors. Now, there's one more thing that I'd like to show you before we finish this video, and it's how to draw the electric field. Now, this is not so important for the gravitational field because at the end all the masses are the same, but with the electric field where you can have positive, negative charges, things get complicated. So it's good to have some set of rules to draw this. Now, let's start with the simplest case. Let's imagine that this is a positive charge and that there's nothing in there. So let's just get rid of that. Now, in this case, the electric field is really obvious. It goes away from this. Because remember from when we did electricity, the electric field shows us what a test charge, which is a positive charge of 1 Coulomb, would do if it was located at that point. So positive charge of 1 Coulomb here, it's going to go this way. You put it here, it's going to go this way, and so on, right? And then I can just keep making these field lines. Now, in order to be a little bit more precise, what we do is the following. If I draw few field lines, like in this case, this means that this charge is not very big. So if I want to make this charge bigger, let's say I have a lot of positive charges, then I'm going to draw more electric field lines. And all this means is that the electric field is stronger. There you go. Now there's another very interesting property of electric fields that I'd like to show you, but for that I need two electric charges. So imagine that I have one positive charge here and another positive charge next to it. And I'm interested in what happens in the middle. So here's my positive charge, and I want to know what happens around here. So the answer is that, well, if I'm a little bit to the right, then this will get pushed this way, but as soon as it gets close enough to here, it's going to start getting pushed the other way, so that at the end, it's going to do something like this, right? And I can draw this way. So it's going this way, and then whoop, this way. And the same will happen for a charge that was placed in here, and then we'll go up, 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 up. And, well, I can do very similar things for any charge that's going up out of here, right? Now, what's interesting about this is that these field lines never cross. And actually that makes a lot of sense, because what if field lines crossed? So imagine that I have here a field line that goes this way, and then another one goes this way. And then I have a test charge right here in the middle. Now remember that the field lines point in the direction where this test charge would go if it was placed here. Okay, so where does it go? Does it go this way, or does it go this way? What we have is a very confused test charge. That makes absolutely no sense. There is only one direction that test charge should be able to go. And therefore, this never happens. Field lines never, ever, ever cross. Another interesting property is that field lines have to start either at one charge or at infinity. And when I draw this, you'll see this much more clearly. So here I have a positive charge, here I have a negative charge, and I wish to know how the field lines are going to look. So this is plus, and this is minus, and then I ask myself again, what's a positive test charge going to do if I put it, let's say, here? And now the answer is very clear. Well, it's going to be repelled by this guy and attracted by this guy. So he's just going to go straight from here to here. And similar things will happen two particles that are positioned anywhere around here, and so on. So as you can see, the field lines start in the positive charge and end in the negative charge. So the takeaway point is very simple. Every field line starts at a positive charge and ends at a negative charge, or infinitely far from the charge. So as always, we end with the learning objectives. Now, a couple of comments about these. This determine the gravitational field due to one or more point charges, and this is what we should be practicing over the next 2 days. So of course I don't expect you to be able to do this straight away, but right now you have the required knowledge to attempt to do so, and that's what we're going to be practicing for the next week. Now this you should already know, but it's part of the learning objectives of this lesson, so I still put it here even though I knew you know already, so that you know it's required in order to study the electric field. Now, I hope this was understandable. Remember, if there's something you don't understand, you can leave a comment, you can email me, or you can just come and ask me during class. Hope that went okay. Bye.